Okay, so now we're at the point where we can actually make some relatively small changes and get a basic molecular dynamics simulation. So there's two main things we need to do. First, we need to change our force equation here to, instead of modeling a spring, we want to model the force between two atoms. And then we want to add lots of atoms together so that we can model a whole system instead of just two objects or two atoms. And then there'll be a few other little things. So we'll do those first two big things in two separate videos. This video will be using an interatomic force function instead of a spring force function. And then in the next video, we'll add multiple atoms and a few other little changes. So just as a quick review, so here is our force function for a spring, where our force is just proportional to the negative displacement. So if we're stretching past the equilibrium distance, we get a negative force that pulls the spring back towards its equilibrium distance. If we compress the spring, we get a positive force that pushes it back towards its equilibrium distance. And if we change the spring constant, that changes the slope here. And so the further you stretch the spring, the harder and harder it gets to pull it an additional unit distance. So that's the force. And the energy of that is the integral. And so if you integrate this force, if you're pulling this in little increments and you add up all those little increments over the distance, you would get the total energy associated with that displacement of the spring. Or alternatively, if you take the derivative of this function, so the slope of this parabola, that will give you the force at that point. And that makes sense because over here where the force is strong, stretching it by a unit distance, because the force is stronger, you have to pull it harder, that's going to increase the energy more than down here where the force is low. Stretching unit distance you're exerting less force over the same unit distance, and so the increase in energy will be smaller. So that's our spring. And for our interatomic potential, when we're close to the minimum, it looks sort of similar to a spring. And when we squeeze really close together, the energy increases really quickly. This is a Lennard-Jones potential, which is a simple model of the energy between two atoms based on how far apart they are. But as you get far away, the energy asymptotically approaches zero. So we set this as our 0 point so that when the atoms are infinitely far away, we say there's zero energy associated with that. When they're at this equilibrium distance, there's negative energy, meaning you have to put energy in if you want to separate them. And if you squeeze them close together, there's positive energy, meaning they're going to want to get out, they're going to push out of that configuration. So this is the energy. And if we take the derivative of this, just like the other one, then we get the force. So here I've just taken the derivative of this function with respect to r. And so this looks similar, but now we're getting the force. And so here at the minimum of the energy function, that's where our force is 0. And our most negative force, meaning the strongest attraction, is here where the positive slope is at its maximum on the energy function. The force also goes to 0 as we go to infinity. And as you squeeze the atoms together closer than the minimum distance, you get a positive force that increases very quickly to push the atoms apart. So this is the force function that we want to use now. Obviously much more complex than this spring potential, but it's just a function of a single variable, r, the distance between the atoms. And we do have these two parameters with which we can model different bond strengths, what the energy well is, and also different bond lengths, but we're just going to leave those both at 1 for now. Okay, so going back to our code, this is the line we want to change because this is our force. And so I'm going to make a new reporter here, and I'm going to call it LJ force, and there's going to be an input, which is r, the interatomic distance. And I'm just going to put in that function that we just saw. It's going to look a little different in the code, but it's the same function. And these ones, I'm just assuming epsilon and sigma are 0, so we have a -4. And here would be sigma, but I'm just assuming it's 1. And so we could actually get rid of this 1, but I'll leave it there for now. And there we go. Okay, now let's test out that this does what we expect. So if I pull this back up here, we'll see that this force function, it should be 0 at about 1.12246. So if I put that as the input here, 1.1246, yeah, we see here that we get almost 0. So to get exactly 0, there's some more decimals here, but here we've got 10 to the negative 4th, so 0.0000117, so it's quite close to 0. If we go to the left of that, like 1, now we're getting a very positive force. And if we go to the right of that, we should get something negative, but that is getting, as we get further and further away, should get closer and closer to 0. And indeed, that's what we see. Okay, so it looks like we put this in here correctly. And now we're just going to replace this. Instead of using this equilibrium distance minus distance myself, we're just going to do the LJ force and distance myself. So we're inputting the distance between the two turtles, and we're getting back this force. Okay, so let's see if that works to model these atoms. So we're starting now 6 away, and it seems like they're not really moving. And that's very far away for this interatomic potential. So let's try making them just 1 away, or let's say 1.1. And now we can see that they are vibrating a little bit there. Let's get rid of the link because we're not going to need that anymore. And let's also set the shape back to be a circle. Okay, so you can see here that we are getting a little vibrating back and forth. If we make them very close, then they're going to repel each other. And since our world wraps around, then they're going to start doing that, which is we're running into some issues. So the fact that it got so sort of crazy there, that's probably because our time step is too big. So I'm going to change this to be a much smaller time step. We can speed our model up here. And now we can see that they're moving back and forth. When they get close to each other, they attract and then they repel off of each other. Okay, so this is our interatomic potential. And in the next video, we'll add a bunch of atoms so that we can have lots of atoms interacting instead of just 2.